think we completed up to 16, right? So now we'll move on to the part. Get so that data. So when they take median. Median is the middle value. Median is the middle value. Median is the middle value of a set of numbers. Median is the middle value of a set of numbers. Middle value of a set of numbers after arranged in ascending order. After arranged in ascending order. After arranged in ascending order. Arranging in ascending order. Okay. Continue next paragraph. If there are n simple n, if there are n number of observations, if there are n number of observations, then median is given by n plus 1 over second observation. Median equals n plus 1 over second observation. Second observation. Second observation. We take some examples. Find the median of the following. Find the median of the following. First one. $45, $63, $95, $21, $52, $33, $10. 2, 4, 6, 7 pages after. So first we arrange in order. increasing order, ascending order, increasing order. So we write the smallest one first. So first it is 10, then we have 21, then we have 33, 45, 62, 63, 95. 4, 4, 6, 7, 9. So first we wrote in increasing order. After that, we have to calculate the observation. So median equals n plus 1 over second observation. I just write obs. N number of pieces. So we got 7 pieces here. So 7 plus 1 over 2 observation. So this will be 8 over 2. 8 over 2 is 4. Fourth observation after ranging. Fourth observation. After ranging, fourth observation. 1, 2, 3, 4. Fourth observation. 40. So median is. So what is the process? The given data set we wrote in the increasing order. Then we identified which number is which observation is the median. Fourth observation, we started counting from here. Fourth observation, 45. So that is the. So here we didn't have any issue because when we calculated this n plus 1 over second observation, we got a full figure. Fourth observation. So we didn't have any issue. Fourth observation, we were able to find. So next we will take example where you get a decimal answer here. Second example. $95, $67, $21, $35, $69, $47, $246, and $39. 2, 4, 6, 8 pieces are there, or even number of observations. So as usual, we have to write in the increasing order. So first we'll write in the increasing order. So we have the smallest one is 10. Then we have 21, 35, 39, 47, 67, 69, 95. I don't know whether I have missed out anything. 2, 4, 6, 8. Yeah. No. So now next we want to calculate the median observation. So median is n plus 1 over second observation. So if we simplify 8 plus 1 over second observation, so it is 9 over 2, 4.5 observation, which is not a full figure. We have fourth observation, we have fifth observation. We want the 4.5 observation. So this is the fourth observation. This is the fifth observation. We need the 4.5. So it will be the middle part of these two. So you take the average of these two. Right here. So what we do, fourth observation plus fifth observation divided by 2. 39 plus 47 divided by 2. I get the answer. So now here you are getting a value which is not even in the data set. You are getting a median value which is not in the data. Now, after doing the two examples, we get this. Two statements. So statement one. Statement one. Is it visible? Statement one. So it says like this. When there are odd number of observation, I just write down observations. The median will be a value from the data set. Median will be a value from the data set. When there are odd number of observations, median will be a value from the data set. First statement. Then the second statement. Statement two. When there are even number of observation, when there are even number of observation, median will not be a value from the data set. So two statements are given. Now we have to see whether these statements are true or false. So first statement, is it true or false? Second statement, is it true or false? So what do you think? First statement. When there are odd number of observation, median will be a value from the data set. So will it be a true statement or false statement? So true when you say it should be always true. False means one instant, if it is not correct, you can say false. So median, what number of observation, your range, definitely there will be a middle value, say 3 pieces. Second piece is the middle one. 5 pieces, third piece is the middle one. So what number of observation when you have, there will be definitely a middle value. So first statement is correct. So the value will be coming from the data set. So this statement is true. So now how about the second one? What do you think? When there are even number of observation, median will not be a value from the data set. Say something like 4 observation, 8 observation, 6 observation, median is not from the data set. Is it true always? Going to our example, we got something like that, but will that happen always? In that case, how we calculated? Fourth observation, that example, fourth observation, fifth observation, we added, we divided by 2, we got the answer. Now, since those two values are two different values, we got a value which is not in the data set. Suppose when you arrange in the middle, if you have repeated values, then you add, divide by 2, still you get the same thing. So this is not always true. Generally, yes, but sometimes this may be violated. So if you want to say false, even one instant you can show that it is not so, then it is false. So here this is false. So when you say false, you have to give a counter example. Counter example we have to give. So if we say something is false, we have to give an example where the statement is violated. So now we'll give a data set, a small data set having or even number of observations in the middle repetition. And give a small data set, maybe with 4 pieces, 5, 10, 10, 20. So it is in order, median, O plus 1 over 2 observation. So it is 2.5 observation. So 2.5 observations, second observation, third observation divided by 2. So it will be 10 plus 10 divided by 2. So we'll still get 10. 10 is from the data. Okay, so we gave a count example where this is violated. So median is the middle value after arranging in order. So next one is mode. Median mode. So mode. So we'll write down this bit underneath. Mode of a set of numbers. Mode of a set of numbers. Mode of a set of numbers is the value. Mode of a set of numbers is the value which occurs. The value which occurs most of the time. The value which occurs most of the time, or with greatest frequency. Or with greatest frequency. Greatest frequency. Right. Find the variables. Examples. Find the mode of the wind. Find the mode of the first one. 279. 279. 576. 279, 279, 576. Mode. Mode means what? The value that occurs most of the time. The value that occurs most of the time. So 2 appears twice. 7 appears 3 times, 9 appears twice, 5 appears once, 6 appears once. So 7 appears 3 times. So move this. Five, 8, 3, 5, 8, 3, 5, 9, 3. 5, 8, 3, 5, 8, 3, 5, 9, 3. Second example. So mode. 5 appears 3 times, 8 appears twice, 3 appears 3 times, and 9 appears once. So mode 5 and 3. 2 modes are there. 5 3 times, 3 also 3 times. Then third one. So in third one, we have 2 parts. Like purposefully, we have these way. So A part. 6, 3, 4. 6, 3, 4. 6, 3, 4. 6, 3, 4, 6, 3, 4, 6, 3, 4. So what do you think? What is the mode? Okay, so we feel like 6, 3, and 4, but it is not so. Why? When you say mode, it should be something special. Now here, nothing is special because all the elements appear same number of times. 6 appears 3 times, 4, 3 also appears 3 times, 4 also appears 3 times. Now see, so here all the terms are appearing the same number of times. So this is no mode. Now see, suppose now if there is a 5, then yes, 3, 6, 3, and 4 are modes. But now here all are appearing same number of times and nothing is special. So this doesn't have a. So if all the terms are appearing the same number of times, nothing is special, then it is no mode. Let me take part 2, 7, take 5, 3, 1, 8, 9. Two, 7, 6, 5, 3, 1, 8, 9, 4. All are appearing only one. Right, so both are similar type. Here, everything appears more than once, but all are appearing same number of times. Here also, all are appearing only once, same number of times. So now from the 3 examples, see some data sets have mode and it has only one mode. Second example, mode is there, more than one mode, multiple modes you have. Third one, data set is there, mode is not there, right? But if you take mean, if you take a data set, there will be a mean. You calculate the mean, there will be a mean, and that will be a unique mean. You don't get 2 means, right? Only one value will be there. So unique. Mode is also, sorry, median is also the same, right? Median, when you calculate for a given data set, there will be a median and it is unique. You don't get 2 medians, right? may be coming from the data set or may not be coming from the data set, but still there will be only one. There will be a median and it will be unique. But mode is unlike that. Some data sets have mode, some data sets don't have mode. Some data sets have only one mode, some data sets have more than. So now we have some terms for this, some technical terms. So we have something called unimodal data set. Unimodal data set. Unique mode, unimodal. Right? If it has only one mode, you call it a unimodal data set. So unimodal data set means what? A data set having only one mode. A data set having only one mode is a unimodal data set. So example 57356. Unimodal, only one mode. 5 is the mode. Then the second technical term is multimodal. Multimodal data set. Multimodal data set. So multimodal data set means a data set having more than one mode. A data set having more than one mode. So a data set having more than one mode. A data set having more than one mode is multimodal. Example 536, 536, 536, 536, 506. So 5 and 6 are modes. Multimodal. So mode means in a data set, the number that appears most of the time is the mode. A data set can have only one mode or may not be having mode or can have more than one mode. If a data set has only one mode, you call it a unimodal, unique mode, unimodal data set. If it has more than one mode, you call it a multimodal data set. So now, under central tendency, we have discussed three things. We discussed mean, we discussed median, and we have discussed mode. Now, what is the relationship between among these three, mean, median, and mode? The relationship. So examples discussed, right? That unimodal, multimodal. Last one. The relationship. Empirical relation. Empirical relation. Empirical relation. So the relationship among mean, median, and mode. So this relationship doesn't exist always. Doesn't exist always. Under a certain condition, it is true. So what are the conditions? It says for unimodal, we know what is unimodal. Unimodal frequency curves that are moderately skewed. Okay, so we'll write down. After that, unimodal part we know, unique mode. It should be having only one mode. That's okay. Moderately skewed, I will explain after writing down. So we'll write down under empirical relationship. For unimodal frequency curves, that are moderately skewed, for unimodal frequency curves that are moderately skewed, mean minus mode equals 3 times mean minus median. Mean minus mode equals 3 times mean minus median. So that's the relationship. Okay. So now by looking at this formula, can we identify? Now we want to find out like this, right? Whether now we have these are 3 components. Mode is there and median is there. So we have the mean is there, mode is there, mean is there, median is there. So now we want to find out whether this mode is closer to the mean or whether median is closer to the mean. Which one is closer? Mean is there, median is there, mode is there. Whether median is closer to the mean or mode is closer to the mean. By looking at this one, can we say which one is closer? There are 3 pieces, right? Mean is there, median is there, mode is there. So 3 values. So now our problem is which one is closer? Is mean will be there. Median is closer to mean or mode is closer to. By looking at this one, you can say. By looking at this line. Mean minus mode means what? The gap between mean and mode. Mean minus median means what? The gap between mean and median. So the gap between mean and median, when you multiply by 3, you are getting the gap between mean and mode. So that means this should be smaller. This should be smaller. This gap is smaller. That's why when you multiply this gap by 3, you are getting the gap between mean and mode. So median is closer to the mean than the. So after this line, you can write down from the above formula, we can conclude that median is closer to the mean. Median is closer to the mean. Median is closer to the mean than the mode. Median is closer to the mean than the median is closer to the mean than the. So now here that conditional statement, unimodal, we know unique mode. Why we need this unimodal? Now see, if it is having multiple modes, we don't know which value to be substituted here. There will be an issue, right? If you have 2, 3 mode values, then which one should be substituted here? We don't know. So that's why it should be unimodal. Now, this skewed, right? So we'll see what that skewed is. Now, if you take this structure is symmetric. The structure is symmetric. This structure is a symmetric structure. Think of, say, jellyfish or something, right? If you push from here, the symmetric property will be disordered if you push from here. So similarly, if you push from here, the symmetric property will be distorted, right? So if you push from this point, so let me take this to the middle. So if you push from here, what happens? The shape will go like this. If you push from here, this has lost its symmetric property. Similarly, if you push from here, the shape will be so it has lost its symmetric property. Symmetric skewed. That is also skewed. So skewness is a measure of symmetric property. So when a structure loses its symmetric property, it is skewed, right? When it is disordered, it is skewed. So this is a skewed structure. This is also a skewed structure. So this is skewed. And this is also skewed. But we can clearly see the two structures are different, right? Now here, in this structure, the longer tail is towards the left. So depending on where the longer tail is, whether it is to the right or whether it is to the left, you define as positively skewed and negatively skewed. So if the longer length or the longer tail is towards the left, you say negatively skewed. So this is negatively skewed. Negatively skewed. If the longer tail is towards the right, if the longer tail is towards the right, then you say positively. Right. So skewness is a measure of symmetric property. So when a structure deviates from the symmetric property, it gets skewed. If the longer tail goes to the left, it is negatively skewed. And if the longer tail goes to the right, it is positively skewed. But they don't say positively skewed or negatively skewed. They say moderately skewed. Moderately skewed means maybe of this kind or maybe of this kind, not in a large scale. Slight deviation from the symmetric property. Slight deviation. Maybe this way or maybe that. Then that equation or the formula holds. Okay, right. So we note down that. Cuteness is a measure of symmetric property. Cuteness is a measure of symmetric property. Cuteness is a measure of symmetric property. If the structure, deviates, if the structure deviates from the symmetric property, then we say it is skewed. Then we say it is skewed. The first up, the following diagram shows the detail. The following diagram shows the detail. Right. So I'll include that also. Longer tail to the right. Longer tail to the right, then positively skewed. Longer tail to the left. Longer tail to the left, negatively skewed. Okay. It's structure. Don't have space, so I can write like there. So in a symmetric structure, mean, median, mode, all are the same point, right? When it gets disordered, only that mean, median will move here and there. So in the positively skewed structure, this will be the order, right? The highest point is the mode. Then we learn mean, mode and mean when you compare, mean and median when you compare, this gap is smaller. So next you have the median. So this gap is smaller than this gap. So there it is with reverse order. Mode, then you have the median. So now see, if all these points are the same, then where for a symmetric structure, that equation won't work because mean minus mode is 0. 3 times mean minus median is also 0. You get 0 equals 0, so no points, right? So only for skewed structures, that is right. So now what is the purpose of that formula? If you know two components, the third component you can find. If you know two components, you can find the third one. So we'll take a simple example on that. The mean and the mode of a unimodal moderately skewed data mean and the mode of a unimodal moderately skewed data are 60 and 69. Find the mean and the mode of a unimodal moderately skewed data are 60 and 69 respectively. I will write respectively. Find the mean. So here the conditions are given: unimodal, moderately skewed. Mean minus mode equals 3 times mean minus median. So mean given 60 minus 59 equals 3 times mean 60 minus median. That's what they're asking us to find. Right. So here it is 9 minus 9. 3, 60 minus median. We can divide by 3. So we get minus 3 equals 60 minus median. So we can take this median to this side and this one to the other. So median equals 60. This goes to the other side plus 3. So any of the two components given, we can find the. But under the condition. What are the condition? Unimodal moderately. Here multiplication. So I brought this 3 down. Minus 9 over 3. So that is 3. This is left on the right side. This minus median I brought to this side. So came as plus median. Minus 3 actually. So goes as plus 3. 60 plus 3. So mean, median, mode discussed. Finally, what is the relationship among the three? The empirical relationship. So that completes chapter 1, measures of central tendency. So now we'll move on to measures of dispersion. Measures of chapter 2. Measures of dispersion. Measures of dispersion. So now, why we need these measures of dispersion? So we'll take a simple example, and through the example, we'll try to identify why we need these measures of dispersion. Right. So now, suppose there are two classes. We'll say class A and class B, two classes are there. And in class A, we'll say there are two students. In class A, there are two students. In class B also, there are two students. After an exam, in class A, one student scored 60 and the other student scored 50. Whereas in class B, one student scored 10 and the other student scored 100. Now we have done measures of central tendency. We can calculate the average. So we are calculating the average here. So if you calculate the average, X bar will say 60 plus 50 divided by 2, which is going to give you 55. Then we say, okay, class A average is 55. Then similarly for class B also we can get the average. X bar B will say X bar A, X bar B will say. So X bar B, 10 plus 100 divided by 2, again we are getting 55. Calculation wise nothing wrong. So later on what we use this value to represent the class. Then we say, okay, class A average is 55, class B average is 55. So now we have to see whether the value we got is the appropriate value. Is that 55 is a good representative value for class A? Is that value 55 is a good representative value for B? What do you think? Does this 55 represent class A properly? Class A average is 55 okay. Class B average is 55. Is it okay? So there is an issue. Calculation wise, nothing wrong. Here, 55 is a good measure. Why? The observed values are closer to the average. So the observed values are closer to the average. So in this case, this 55 is a representative value of this class A. Here, one student is extremely good and the other student is not. But still the average is 55. There is nothing wrong with that 55 value. But that 55 doesn't reflect this, right? So when we are given a data set, we got the calculator, we have the formula, we can calculate anything. After calculating the mean, we have to check whether it is a good measure or is that value, is the central tendency value properly represent this group or whatever. We have to check. For that, you need another measure. That's why we have these measures of dispersion. So for everything, we have a reason. We calculate the mean. Then we need to check whether the mean is the proper value to represent the class. For that, we need another measure. So measures of dispersion. Okay. Measures of dispersion. So this is chapter 2, right? Chapter 2. You can take up this page. There are several measures of dispersions. There are several measures of dispersions. There are several measures of dispersions defined in statistics. There are several measures of dispersions defined in statistics. The following are some of the measurements, some of the measures of dispersion. Some of the measures of dispersion. The following are some of the measures of dispersion. Some of the measures of dispersion we use frequently. We use frequently. So these are the ones. Range, interquartile range or quartile and quartile deviation, mean absolute deviation or mean deviation, standard deviation, coefficient of range, interquartile range, quartile deviation, mean absolute deviation or mean deviation, standard deviation, coefficient of variation. So we'll discuss one by one how it is defined, how to can. So one by one we'll discuss. So first we'll take range. So range has two definitions, right? Range has two definitions. So range is defined as highest value minus lowest value plus 1 for ungrouped data. So range is defined as highest value minus lowest value for group data. Okay. So we learn in a different way. So we learn, right, like we said, discrete type data, discrete, we said, frequency data, we said, and group data, we said. Now here they say ungrouped group. So that means this discrete and frequency fall under ungrouped. So if your data set is discrete or frequency, then it falls under ungrouped. So you have to use this formula. Only for group data. So the two definitions. Highest value minus lowest value plus 1. Highest value minus lowest. I will take a So find the range in sales of shop A and B. Find the range in sales of shop B. So I think in a problem sheet, this problem is here. Remember the number. So two series are given, sales figures, shop A, shop B. So they're asking us to find the range in sales. So two data series. So we have to see what type of data set is this. So this is a discrete type, just values given, discrete type. If it is discrete type, then we know it falls under ungrouped category. For ungrouped category, this is the formula, highest value minus lowest value plus 1. So in this series, we identify the highest value as 1120, lowest value as 990, then that plus 1. We got the calculated advantage. So similarly for shop B range, highest value minus lowest value plus 1. So according to the data set, you have to identify which formula you need to use. Okay, another example. Find the range of number of students 5 to 10, 10 to 25, 25 to 30, 30 to 40, 40 to 50. 3 students, 7 students, 9 students, students. So find the range of that data set. So it's a group data. So for group data, range is highest value minus lowest value. This is how it is given. So now in this data set, can we identify the highest value? We can't identify the highest value. Now say in the original data set, if the highest value is 40, 40, 40 we'll say, right? If you have 40, then that will fall into this category, In the original one, if you have 45, then that will also fall into the same category. So we can't identify from this type of data, we can't identify the exact highest value. So in this formula, though it says highest value, it is not the highest value, it is the highest possible value. Lowest value, again, not the lowest value, lowest possible value, value, right? But it is not the exact value. So that's why now we are not sure of this highest value. We are not sure of this lowest value. There's no point in using that +1 adjustment. So that's why in this formula that +1 is dropped off. Right? No point, right? So here, though we say highest value, it is not the highest value. It is highest possible value. Highest possible value. Lowest means not the lowest, it is the lowest possible value. Now, if we take that way, then we can write this as highest possible value 50. Lowest possible value 5. Then it is 40. Here, this is the highest possible value. Highest possible value. Lowest possible value. So next we'll go into interquartile range and quartile deviation. So in short, interquartile range, IQR, quartile deviation is QD, short form. So IQR is interquartile range. QD is quartile deviation. Two different measurements, but one is in relation with the other. One is a multiple number. So how this is defined? So this IQR interquartile range is defined as Q3 minus Q1. Interquartile range is defined as Q3 minus Q1. Quartile deviation is defined as half times Q3 minus Q1. So what is this Q3? What is this Q1? So Q1 is the first quartile. And Q3 is the third quartile. IQR is defined as Q3 minus Q1. QD, quartile deviation, is defined as half times Q3 minus. So that Q1 is the first quartile, Q3 is the third quartile. So what is meant by first quartile? What is meant by third quartile? I will explain. So now we have to see what that first quartile and third quartile are. What those first and third quartile. So this first quartile, third quartile. Now when you are given a data set, you can arrange the data set in increasing order. So smaller values will be on this side. So this side you have the small values, and that side you have the large values. So you can arrange the data set in increasing order or ascending order. Then you can identify 3 points. Which divides the entire data set into 4 equal parts. Right? You can identify 3 points which divides the entire data set into 4 equal parts. So we divide may not be in equal size, right? But assume, right, all are the same, right? So you can find 3 points such that the entire data set is divided into 4 parts. So that means 25% of the lowest data set will be in this region. The next 25% will be in this region. 25% of the data set will be in this region. The third 25% will be in this region. And the largest 25% will be in this region, 25%. So we can find 3 points which divide the data set in this manner. Smallest 25% here, largest 25% here, second 25% here, and the third 25% here. So these 3 points when you take, one will be smaller, one will be larger. So out of these 3 values, the smallest value is called the first quartile. So this is called the first quartile. And this is called the third quartile. So if you have the first quartile and third quartile, then this is the second quartile. So this first quartile you denote by, Q1, first quartile. This one you divide by third quartile. Second quartile is Q2. So for the formula, we need this first quartile and right. So when you are given a data set, you arrange in increasing order, identify 3 points, which divides the entire data set into 4 equal parts. Out of the 3 values, the smallest value is first quartile, largest value is third quartile. In between, you find the second quartile. Right. So now how to get this quartile? First quartile, how do we get? Now for median, we have a formula n plus 1 over second observation. So here also we have a formula like that. So what is the formula? For first quartile, this is first quartile. Q1 is 1 over 4 n plus 1 observation. After arranging 1 over 4 n plus 1 observation. So third quartile is 3 over 4 n plus 1 observation. Right. So that's the formula you use to get the first quartile and third quartile. Okay. So we'll draw the structure and without writing much. Yeah. Let's draw this, then we can. Entire data set, you arrange in order, increasing order, identify 3 points. Out of the 3 points, the smallest one is first quartile, largest one is third quartile. When these 3 points are found, the data set should be divided into 25%, 25%, 25%. So what we call as the second quartile is the median, right? Second quartile is the median. So now we'll take a simple example and see if we are given a data set, can we find this Q1, Q3 and the IQR and QD? Find the interquartile range and quartile deviation of the following. 25, 96, 43, 52, 31, 205, 68, 11, 2, 4, 6, 7 pieces. So we are asked to find IQR and QD. So to get these values, we need the first quartile and the third quartile. So to get the first and third quartile, first of all, we have to arrange it in increasing order. So we'll arrange in increasing order 11. 11, then we have 25, then we have 50 or 31, 43, 52, 68, 93. Sorry, 93. 2, 4, 6, 7. So now we are going to calculate Q1. Q1 is what? 1 over 4 n plus 1 observation. So it is 1 over 4, 7 plus 1 observation. So it is 2 second observation. Second observation. So after arranging second observation, so this is the second observation, 25. And third quartile, 3 over 4 n plus 1 observation. So 3 over 4, 7 plus 1. So it is sixth observation. After arranging 1, 2, 3, 4, 5, 6. So this is the sixth observation. So that is 60. So we found the first quartile, we found the third quartile. So now we want to find the IQR and QD. We have the formula, so substitute in the formula. Here. So IQR. Q3 minus Q1. Q3 is 68 minus 25. So that is 3, 43. Interquartile range is 43. So then we go for the other one, quartile deviation. Quartile deviation is half times Q3 minus Q1. So it is 1. You can substitute. Final answer will be 21.1. So interquartile range, quartile deviation. So in this example, we didn't have any issue because when we divide this by 4, we got a full figure. But this doesn't happen always. Here also we got a full figure. It doesn't happen always. So if it doesn't happen, then how to we calculate? We'll take the next example. Find IQR and QD, right? $45, $63, $71, $77, $93, $46, Q4, $58, $32, $4, $8. So first of all, we have to arrange in increasing order. So we'll do that first. So the smallest one out of all this is 13. 13, then we have 45, then 46, 58, 63, 71, 77, 93, 2, 6. So first quartile. First quartile. 1/4 n plus 1 observation. So it is 1/4 8 plus 1 observation. So this is 2.25th observation. So we are not getting a full figure, we are getting a decimal value, 2.25 observation. So we have the second observation, we have the third observation, but what we want is 2.25th observation. So this is the second observation. This is the third observation. Right. So this 2.25 means it has passed the second observation. It has passed the second observation, but not reached the third one. That is 2.25. So this 0.25 tells us that in the gap, in this gap, it has covered 25%, right? 2.25 means it has passed the second observation. This 0.25 tells us that it has covered 25% of this gap. So how do we get the value? This full figure tells you the observation number 45 plus 25% of the gap, this gap, 46 minus 45. So this is 45 plus 0.25, 45 point. Right? So 2.25 pass the second one, not reach the third one. 25.25 tells us 25% of this gap it has covered. So 25.25, 46 minus. So you can get the value. So similarly, you go for the other one. Third quartile. 3/4, 8 plus 1. So it is 6.75th observation. So this tells us that it has passed the sixth observation but not reached the seventh one. So this is third, fourth, fifth, sixth. So this is your sixth. This is your seventh. Right. So pass the sixth observation. So 71 plus 75% of this gap. So 0.75 into 77 minus 71. So it is 71.75 into statement. So now Q1, Q3 known. So you are requested to calculate IQR and QT. Substitute calculate. So that was the target, right? Get the Q1 and first IQR and QT. These two values. So here, what I put it not clear here. So this is 71.75 into here it is. You can get that. But finally, you asked to find IQR and QD. So you have the third quartile value, you have the first quartile value substitute. So that is IQR and QD. So sometimes like when you do kind of data collection, after collecting the data, right? After collecting the data, you find the range, right? Then you calculate the Q1, you calculate the Q3, then you dispose this data. Part and this part you remove and you use only this portion for the value. Right? So then you get a good result because the extreme values are intact. So it's a quartile range and quartile deviation. How IQR is defined? IQR is Q3 minus Q1. Quartile deviation is half times Q3 minus Q1. We discussed both of these under the same heading because you can clearly see it is the same thing, multiple of the other. Next one. Mean absolute deviation or mean deviation. Mean absolute deviation or mean deviation. Right. So if you use this mean absolute deviation, then the abbreviation is MAP, the first letters of each term. Mean absolute deviation. If you use it as mean deviation, then D, mean deviation. Both are the same. Mean, if you say mean deviation or mean absolute deviation, it is the same. So how this is defined? How this is defined? So this is defined as either you can call it as mean absolute deviation or mean deviation still. So this is defined as 1 over n sigma modulus x minus x bar for a discrete data. So you read these two vertical lines, you read as modulus. Modulus. One over n sigma mod, in short you read this as mod x minus x bar or modulus x minus for a discrete data. For a discrete. So what is this modulus? So modulus is, now see if you take mod of phi, so this is phi. Mod of minus 3 is you take just the magnitude, you ignore the sign and you take only the magnitude. So if you have something like say 3 minus 7, mod 3 minus 7, internally if you simplify, 3 minus 7 is minus 4. What you have is mod of minus 4, so this becomes mod of minus 3.9. So this is just 3.9. So whatever it is, you just ignore the sign, you take only the magnitude. So that is modulus. So now we'll take an example for this mean absolute deviation or mean deviation. So they are asking us to find the mean absolute deviation of this data. So when you take down the data set, you better take down this data set as a column. So the values are here, x values. So X values are there. 1120, 990, 1040, 1030, 1105, 1015. Those are the values. Right. Now, what is the formula we are going to use? We are going to use mean deviation or absolute mean deviation. 1 over n sigma mod x minus x bar. So to use this formula, first we need to get the x bar value. X bar is sigma x over n. So first we need the sigma x. These are our x values. So we add this. If we add this, we get sigma x. 5, 5, 10, 10, 16, 20, 2, 3, 4, 9, 13, 1 left, 2, 3, 4, 5, 6. 6,300. So now we can get the x bar value. So x bar is 6,300 over n. How many pieces? 2, 4, 6 pieces. So this is 1050. If you simplify, x bar comes to 1050. 6,300 over. So now we need the sum of mod x minus x bar. So before finding mod x minus x bar, we need x minus x bar. So we calculate x minus x bar. So first we calculate x minus x bar. From each, we subtract 1050. So this is 70 minus 60 minus 10 minus 20, 55 minus 35. From each of these values, we subtract the x bar, that is 1050. So now next we want the mod of x minus x bar. So mod x minus x bar. So nothing to do, just whatever you have here, you have to take the modulus. So positive 70, 60, 10, 20, 55, 30. So now we want that sum. So we'll add this. If we add, we get sigma mod x minus x bar. 5, 5, 10, 4, 9, 10, 18, 25, 250. So now we can go for this formula. Deviation 1 over n sigma mod x minus x bar. 1 over n, how many pieces? 6 pieces. And this sum, just now we calculated that 250. So 250 over 6. 24 tens, 41 point. 41.6. mean absolute deviation. So now, what is the meaning of this mean absolute deviation or mean deviation? So see the way we have calculated this. So now we had a data set, right? Points were like this here and there, right? 6 points were there. Okay. Then we calculated the average, right? We calculated the average. Right. So we'll say the located average is somewhere here, we'll say. So this is our X bar value. Then what we did, we calculated the X minus X bar. X minus X bar means what? The gap between the observed value and the X bar. So we calculated these gap. These are the observed values. This is the mean. So we calculated these gaps. Right? These gaps we calculated. Then some gaps are positive and some gaps are negative. Some are positive, some are negative. If we add as it is, what happens is this sum will be zero. Right? This sum will be zero because some are positive, some are negative. Internally they get cancelled. Right? So what we did is by using this modulus, we made all the values to be positive, all the gaps to be positive. We made all the gaps to be positive. Then what we did, we added all the gaps, right? So we found the X bar value. Then we found the gap between X and X bar. Some are positive, some are negative. Then using this modulus, we made all the values to be positive. Now we have the gaps, all the gaps. We added all the gaps. Then we divided that by number of gaps. So what we have here is the average gap. Average gap between the observed values and the mean value, right? So when you calculate this mean deviation, relatively if you get a smaller value, right, when compared to X bar, right, when you calculate the mean deviation, relatively if you get a smaller value when compared with X bar, then X bar is a good value, right? Because we want to check whether X bar is a good representative value. Make a value of what was the X bar value? X bar value was 1050. What is the mean deviation value? 41.6. So relatively mean deviation is small. So relatively when you compare with the X bar, if mean deviation is small, X bar is a good measure. If make 1050 when I got to make a 10,000, then there is an issue. Right? You can't have, there is no rigid rule like it should be below this amount. No, there's nothing like that. Relatively, you check. If the mean deviation is relatively smaller, then it's a good measure. Then we go for the standard deviation. So this is the measure we use frequently. Always, whenever you give a mean value, average value with the mean value, you have to give the standard deviation. Right. So standard deviation. So here also we have to discuss like we did in the mean. So mean we said we can have population data, we can have sample data. Then three different types of data: discrete, frequency, true. So here also those 6 categories are there. You can have population data, you can have sample data. Population discrete, population frequency, population group. So similarly on the other side, sample discrete, sample frequency, sample frequency. So like in mean, 6 formula for standard deviation. Okay, right. So put the heading as standard deviation. After that, we fit. This is the measure. This is the measure. We use. This is the measure we use as the dispersion measure. As the dispersion measure. Most of the time. Most of the time. Of the time. The time. Full stop, continue. Whenever we are giving the mean value, whenever we are giving the mean value, whenever we are giving the mean value, we are giving the mean value. With the mean value, we have to give the standard deviation value. We have to give the standard deviation value as well. We have to give the standard deviation value as well. Example. The company has a mean sales of LKR, sales of LKR 15 million with a standard deviation of 1.2 LKR, right? LKR 1.2. So with the mean value, we give the standard deviation. Right? That's how we don't just give the mean value. Mean of this much with the standard deviation. Whatever the unit you use for the say mean will be the same unit for standard deviation. Right? The next para you can take down. According to the type of data, according to the type of data, the notation for standard deviation, according to the type of data, the notation for standard deviation varies. So we use S for sample standard deviation. Sample standard deviation. S we use for sample standard deviations. Then we use sigma for population standard deviation. So sigma, you write like this, sigma. So this is sigma. So we have two sigmas. This sigma, we have this sigma, and we have this also. This is capital sigma, uppercase letter sigma, and this is lowercase letter sigma. Capital sigma, simple sigma. Capital sigma we use for summation, additions. Simple sigma we use for standard deviation. Right. A sigma, this is not the way it is written, right? So sigma is something like this. Okay. So I used to write this way. So this is what I mean here. Capital sigma, simple sigma. So simple sigma we use for standard deviation. So now we'll look at the formula for standard deviation. We have population data, sample data, population data, sample data. So this way we have discrete, frequency, discrete frequency. So population discrete, population frequency. So we have all the things. So first one, if it is population discrete, then sigma equals sigma x minus mu whole thing squared over n. Don't forget the square root of the whole. Right. Population discrete data. Sigma equals square root of sigma x minus mu whole thing squared over n. So if it is sample discrete type, S equals sigma x minus x bar whole thing squared over n minus 1 square root of the whole. Formula is different, right? See, here it is n, there it is n minus 1. Here it is mu, there it is x bar. So if we have population frequency data, sigma equals sigma f times x minus mu whole thing squared over sigma f square root of the whole. So if it is sample frequency, S equals sigma f into x minus x bar whole thing squared over sigma f minus 1 square root of the whole. So here it is sigma f minus 1. Population group sigma equals f into m minus mu whole thing squared over sigma square root of the S equals sigma f m minus x bar whole thing squared sigma f minus 1. Yeah. So this is m minus x bar. So no need to memorize the formula. Formula will be given, but you should know how to work out and get those values. So find the standard deviation of the following data set. Okay, so here I'm going to change one value. So this 8 we take as 7. Then you get a full figure as the x bar, right? Otherwise, with decimals, you have right? 2, 3, 4, 5, 7, 4, 3, 8, 15, 20, 23, 27, 30, 31. So when you take down this data set, better take down in the column. So your X values are 3, 4, 5, 7, 4, 3, 4. Space is not enough. Finish. So now what type of data set is? Nothing is given. So we have to assume that this is a sample data. Sample data. Okay, what is the type? Discrete as well. Sample discrete type data. Now in our table we have the formula. So what is the formula? It equals sigma x minus x bar whole squared over n minus 1 square root of the whole. So to evaluate this, first of all, we need the x bar value. So we need to get the x bar first. X bar, what is the formula? Sigma x over n. Right. So we have the x column. We can get sigma x. If we add this column, we get sigma x. So here 5, 10, 14, 21, 25, and 7, 32. Sigma x is 32. How many pieces are there? 32 over 2, 4, 6, 8 pieces are there. So this is 32 over, it is x bar is 4. So now we got this value. Now we need this sum. What sum? X minus x bar both in squared sum. So step by step we'll develop. So first we'll calculate x minus x bar. Then we can move for x minus x bar whole in square. So from each of this value, we know the value x bar 4. Subtract 4 and write down. So 2 minus 4 minus 2 minus 1, 0, 1, 3, 0, minus 1, 0. Right. From each of this value, subtract 4 and 8. Now what we want to get? Minus 2 squared 4. 1, 0, 1, 9, 0, 1. So each of this value you squared. With the sign minus 2 squared, so it becomes 4. So here 5, 6, 7. So sigma x minus x bar whole thing squared is 16. Right. So now see, this is another technique. Now earlier case, mean deviation, we calculated x minus x bar. Some are positive, some are negative. So we took the modulus and made it positive. Positive that is one way. You take the modulus and now this is the other way. You square, right? When you have positives and negatives, if you square all the values become. So this is another technique, two different techniques, right? So now we got this sum. So now we can substitute. What is it? Top part, this square is 16. Over n is 8 minus 1. Square root, don't forget that. So it is S is 16 over 7 square root. You will have the calculator. So get the value up to 2 decimal place, properly rounded, right? Whatever it is, dot cross 2 decimal places properly. No? Maybe 1 point. 1 point. 1.5. 1. Okay. So now we found the mean. So how do we, sorry, have a standard deviation we found. So how do we write the statement? So we give in one statement like the mean with the standard deviation. So this data set, right? The data set given as a mean of the data set given has a mean of, we calculated mean of 4 with a standard deviation of 1.51. The given data set has a mean of 4 with a standard deviation of 1.51. So now when you compare, this is your mean value, this is your standard deviation value. So relatively the standard deviation is 4. So this 4 is a good value for this data. Right, so there is no clear-cut rigorous things, right? If it is more, it's true. That's how. Okay. Another example. So this is the example of frequency. So the question is not there. Find the standard deviation. Find the standard deviation of the following data. Find the standard deviation of the following data. So first we have to get the mean, right? So This is a frequency type data. Nothing is mentioned, so this should be a sample data, sample frequency data. If it is a sample frequency data, then the formula we use for X is sigma F times X minus X bar whole squared over sigma F minus 1 square root of the whole. Sigma F minus X bar whole squared over sigma F minus 1. So for this one also we need X bar. Frequency type data. How do we get X bar? X bar is sigma Fx over sigma. So the required columns we have to develop. So number of employees absent is our X. Number of days is our F. So we need to generate Fx column. Fx. 2 into 2, 4, 12, 12, 20, 18, 21, 20. So we add all these to get sigma Fx. It is 2, 8, 16, 20. 5, 13, 15, 15 plus 2, 17, 17 plus 4, 21, yeah, correct. 21, then 4, 6, 8, 10, 11, 111. And this number of total frequency 6, 9, 13, 13 plus 9, 20. So we can substitute here 111 over 22. So it is 5.05. That's the X bar value. you can get the values. Yeah. Right, then each value you spare. Add all values, get the sums. Minus x bar. Minus x bar with h square. Then we need f into x minus. F get all these. Yes, we can do that. the values are there. F into x minus x bar will be square of sum sigma f. Now it's just a matter of substitution. First, sigma f into mod x minus x bar whole square over sigma f minus 1. Yes. So this sum we got 78.955 over 22 minus 1. Yeah, you got the calculators to evaluate at the appointment. So like earlier case, we have to write down that statement. Like the given data shows the mean of 5.05 with the standard deviation of 1 point. That is given data set shows the mean of 5.05 with the standard deviation of 1.9. So we have done a discrete type, how to get the standard deviation. We discussed a problem on frequency type. So the other type is group. Group type is also something very much similar to this. Only issue with only problem thing is instead of this X, you will be using the M class midpoint. So I give you that as the homework. So you can try when you have free time again. Find the standard deviation. Find the standard deviation of the Padovic table. A simple data set. Nothing is mentioned, so this is a sample group type data. So you will be using the formula as equals sigma f m minus x bar whole thing square over sigma f minus 1 square root. To get this x bar, you use sigma f m over sigma. M means class min. Only one step is there to detect the coefficient of variation. So we'll discuss that in the next one. Here. දැන් ස්ටොක් ප්‍රසෙන්ටිං එක තමයි.
Review. හරි.
ඒක තමයි නෑ උදන්ට යන්න බැරි වුණා අපිට. ස්ටොක්